Dear student, I welcome you for the lecture series in chemical equipment design. Today we are going to discuss the power requirement for agitation system. So in general, power is one of the most important factors that is essential to be studied when we consider the process of mixing or agitation. So the energy requirement for mixing operation that depends on various factors, that is which type of the mixing is to be carried out, whether it's a dispersion, dissolution, crystallization or a chemical reaction. Not only that, it also depends on the physical properties also. When you talk the physical properties such as density, viscosity, the liquid height in the tank, agitator type, that is whether it's a propeller, whether it's a turbine, whether it's a paddle type or an anchor type, then what is its speed of rotation, then what is the vessel diameter, whether the baffles are present or absent. So all these are the different factors that is to be considered for calculation of the power requirement. Now, to calculate this power requirement, it is done based on certain correlations. That is the power number, the Froude number, and the Reynolds number. So, in general case, for Newtonian fluids, this is for Newtonian fluids, the power consumption can be correlated by dimensional analysis. So what is this dimensional analysis? That is, you have already studied that in the mathematics. Now first we will consider what are the functions or what are the different parameters or what are different variables that are dependent on the power. So power, that is a function of viscosity, density, gravitational force, speed of rotation and the vessel diameter. So these are the basic physical parameters that are taken into account for the calculation of the power. So power that is dependent or is a function of this viscosity, density, gravitational force, speed of rotation and the diameter. Then according to the pi theorem, the required dimensionless relationship, that is pi 1, pi 2, pi 3, which is equal to the 0, where pi 1 is the function of pi 1 and pi 2. These are all the dimensionless numbers. So we are interested in finally calculating a dimensionless number. So our basic relationship power, which is taken as the constant, and viscosity raised to A, density raised to B, gravitational force raised to C, speed of rotation raised to E, and the diameter raised to F. So we have written in this relevant quantities. Now we must know the units of all these to make a dimensionless number, to understand the units, to make a dimensionless number. So writing down the power, what is actually power? Power is written in terms of the watts. Watt is nothing but the joules per second. And what is joules? That is the Newton meter. Joules is Newton meter. So watt becomes joule per second. This will become equals to the Newton meter per second. Now what is Newton? That is the mass into the acceleration. That is the kg into meter per second square. So finally your power units, that will become kgs into meter square per second cube. The next is the viscosity. Mu, that is the viscosity. Mu is having the units of Newton second per meter square. Newton second per meter square. So Newton is nothing but your mass into acceleration, that is kgs into meters per second square. So after simplification you get kgs upon meter second. G density is kgs per meter cube, that is written as it is. G acceleration due to gravity, that is meters per second square. N nothing but the speed of rotation, which is 1 upon seconds. And d the diameter, which is written in terms of the m. So by comparison of these exponents of the identical units, three equations in terms of five variables, they can be written as. Now what is this? Identical units. So units are to be taken into account or has to be considered. So collect kgs. Now consider this kg, it is having raised to the power nothing. But this kg is having the raised to the power a, this kg is having raised to the power b, and rest doesn't have the unit of kgs. So a plus b, which is equal to 1, this is raised to the power 1. Then the second is the second, collection of the seconds. So this is the second cube. So this equation, second equation, is for the seconds. This is the cube, 3 that is coming into picture. Then second raised to minus 1. This 3 is also minus 1. This second raised to minus 1. This second square, that is 2c. Again this 2c is also minus. And second raised to minus e. So making all negatives, that becomes positive, a plus 2c plus e, which is equal to the 3. The next is collecting all m. M, that is the meter square. So this is making the minus 2 and rest are making the plus. So meter raised to a, meter cube, that is 3b, then meter raised to minus c, and meter raised to minus f. So this equation becomes a plus 3b minus c minus f. That is, all these three equations are collection of all your kgs term, collection of all your second terms, and collection of all your meter terms. So this above equation can be solved relative to any three quantities, assuming that the other two are fixed. Now simplifying this. So writing this equation in terms of a and c. This is more important. Writing this above three equation in terms of a and c. That means you are going to eliminate b, e, and f. So b is written as 1 minus a from the first equation. E, that is written as 3 minus a minus 2c, and f, that is written as 5 minus 2a minus c after simplification, substitution of the b in this equation from first. So it becomes equal to minus 2a minus c. This is the simple substitution, that is, we are writing in terms of a and c. All the three equations are written in terms of a and c, so that we are going to eliminate b, e, and f. So you will get mu raised to a, then rho raised to 1 minus a, g raised to c as it is, n raised to e, which is nothing but 3 minus a minus 2c, and d raised to f, which is nothing but 5 minus 2a minus c. Now you have to rearrange these things and collect all A, collect all C. So collecting all A will give you the d square n rho upon mu raised to minus A. Collecting all C, that is d n square g raised to. So all these equations and collecting the p terms, p and the constant, this rho raised to 1, then n raised to 3 and d raised to 5. So all the different terms which are having the constants, they are collected in 1. All A are collected in one term and all C are collected in one term, so that you will get P upon rho n cube into d raised to 5. This is nothing but the NP, that is called as the power number. Then d square n rho upon mu, that is nothing but the Reynolds number, and dn square upon g, that is the Froude number. So this is a relationship or a power relationship representing the Reynolds number and the Froude number. Np, which is equal to the constant, Reynolds number raised to minus A, Froude number raised to minus C. So it can be seen that the viscosity mu and the gravitational constant g are accounted only once and each only in the dimensionless number. So for that purpose, the power number and Reynolds relationship, that graph is to be plotted. So this graph related to the Reynolds number and power number, that we will see. So this is the graph that will be plotted as NP power number versus the Reynolds number. That is the power correlation for various impellers and baffles. Now at lower Reynolds number value, that is from 1, 10 and 100, 1, 10 and 100, the Reynolds the power number values, they are not varying much. If you think 1 to 10, it is more or less constant. The power number is almost the same. However, the power number varies drastically at higher values of Reynolds number. That means higher the speed, higher the turbulence, higher the rotation, you require, or variation in the power number is to a larger extent. So this is important point to be noted. That is, at a higher Reynolds number, the power number or the power required is going to vary drastically. Now all these different curves 1, 2, 3, 4, 5, 6, they are for various types of impellers and with or without baffles. Say for example the propeller with baffle, propeller without baffle, turbine with baffle, turbine without baffle, turbine with the disc and turbine with disc and without baffle. So these different curves are there for different types of the impellers. So depending on the type of a impeller, your power consumption, that is going to vary. So such type of power relationships, they are available. Now when you do or calculate something, you will require the power number and the Reynolds number relationships, or such graphs they are required. And if you will calculate the Reynolds number, because you will be knowing the diameter, speed of rotation, the density and the viscosity. Density, viscosity, that you are knowing. You are knowing the diameter, and n is the speed of rotation. What will be the speed of rotation? That will be decided by the operator. So how much power that will be consuming, that you can calculate from this graph. So if the 1000 is the Reynolds number for a typical value for the say sixth curve, the power required will be approximately zero point 0.4 units. It's a unitless, dimensionless number, zero point 0.4. From there you can calculate the actual power, because the density values you are knowing, the speed rotation you are knowing the diameter. From there you can calculate this power. So this is the use of your power correlationship between the power number and the Reynolds number.